So we're continuing onward with our my presentation of some various topics you could look at. This one we're looking at highly connected graphs. So we've already seen various forms of connectedness in graphs. For example, just a graph being connected, non-separable graphs. We've talked about the connectivity of a graph, so number of vertices required to be removed in order to disconnect the graph. This week we're getting into, in our normal material, we're getting into Hamiltonian graphs. So that'll sort of be our launching point. We'll talk about Hamiltonian graphs this week. Remember, or maybe you haven't watched the material yet, but a graph is Hamiltonian if there exists a cycle in the graph which encounters every vertex of the graph. So that's a Hamiltonian graph. And then one thing we'll get into next week is the idea of a Hamiltonian connected graph. So we'll also encounter the term Hamiltonian path this week, and that is a path in a graph that encounters every vertex of the graph. And we say a graph is Hamiltonian connected if there exists a UV Hamiltonian path for every pair of vertices U and V in the vertex set. So no matter what pair of vertices you pick, you can find a path between them that encounters every vertex of the graph. So that is a very highly connected graph, this idea of there being a Hamiltonian path between any two vertices. And we'll encounter this next week in section 6.4. But this idea of Hamiltonian connectedness, I've worked on two research projects that use this, two sort of attempts at generalizing the idea of a graph being Hamiltonian connected. And so I'll look at these in the next couple slides. So the first is a Ktree connected graph. So a graph is said to be Ktree connected if for every set S of K vertices of G, there is a spanning tree of G whose leaves are exactly the vertices in S. So, yeah, we say graph is, so for example, if I say graph is two tree connected, if a graph is two tree connected, that means for every pair, every set of two vertices of the graph, there is a spanning tree of G whose leaves are exactly those two vertices, but a spanning tree with two leaves is just a path, right? And so that's equivalent to finding a spanning path whose end vertices are U and V. But a spanning path, that's a path that involves every vertex of the graph. And so that is a Hamiltonian path. And so a two-tree connected graph is really the same thing as the graph being Hamiltonian connected. And so we generalize this to, in general, so let's say three-tree connected would mean any set of three vertices, I can find a spanning tree whose leaves are exactly those three vertices. So given any set of three vertices, I can find a spanning tree that does this. So that's the idea of a Ktree connected graph. And the unsolved problem here that we ran into comes from this idea. So we'll see later next week that if a graph is Hamiltonian connected, then it's also Hamiltonian. So Hamiltonian connected is a stronger property than Hamiltonian. And it seems likely from our research that if a graph is Ktree connected, then it should also be K-1 tree connected. However, we were never able to prove or disprove this result for even the simplest case when K is equal to 3. So if a graph is 3-tree connected, that implies it's 2-tree connected. We weren't able to prove this nor disprove it. So this would make a nice topic to look at some graphs, find a graph that's, say, 3-tree connected, and see if it's 2-tree connected or not would be a nice special case of this, and to just do a little bit of work on this topic. And that's our conjecture here. So it's possible that you could find, I mean, this is one that you could actually, if you worked really hard, you might actually be able to publish a paper with me on it. If you're able to, for example, find a graph that's 3-tree connected but not 2-tree connected, that could be the subject of a paper. I think we could write a paper on that. Not that you need to do this in order to get a good grade on this project and succeed on the project. You don't need to get some kind of publishable result, but just sort of letting you know that this one definitely has some room, some paper opportunities here. All right, another attempt at generalizing Hamiltonian connectedness is the uniform spectrum of a graph. So we say that a graph is K uniformly connected for some K between 1 and n-1 if for every pair UV of vertices, there is a UV path of length k. So how does this generalize Hamiltonian connectedness? Well, if we set k equal to n minus 1, then what we're asking is for every pair of vertices, there is a path of length n minus 1. But a path of length n minus 1, well, that has n vertices in it, and so this would be a path that encounters every vertex of the graph. And so if a graph is n minus 1 uniformly connected, then that's the same as it being Hamiltonian connected. So these are the same idea. This generalizes it because now we can choose different values of k and see if a graph is k uniformly connected. Now the uniform spectrum of a graph is the collection of all those integers k for which g is k uniformly connected. So a graph being Hamiltonian connected is the same as having n minus 1 in its uniform spectrum. It's an element of its uniform spectrum. And so we've looked at this for various graphs. We've determined uniform spectrums of large classes of graphs. I'll mention a few of those here, and then I'll get to the conjecture. So the complete graphs, this is sort of an easy example. Complete graphs. Let me pick a different color than red. So like take K4 for instance. And observe that between any pair of vertices you pick, you can find a path of any length between 1 and n minus 1. So between these two vertices, I can find a path of length 1 because they're adjacent, right? Being adjacent seems to have a path of length 1 between them. There's a path of length 2 between them. There's a path of length 3 between them. And that's the case for any pair of vertices here. We can find a path of every possible length. So that means that that complete graphs have a full uniform spectrum. Every possible k is in their uniform spectrum. And in fact, they are the only graphs that have full uniform spectrum like this. Any bipartite graph has an empty uniform spectrum. So if you take, for example, let's look at K33. Here's K33. And what I'll say is going to be true for any bipartite graph, but I just want to mention it. Between any two vertices in the same partite set, you can only ever find a path of even length, 1, 2, or 1, 2, 1, 2, 3, 4. Right? There's only even length paths between vertices in the same partite set. There's no paths of odd length between two vertices in the same partite set. So what that means is no odd integer can be in the uniform spectrum. Bipartite graphs are not k uniformly connected for any odd k. And then any two vertices in opposite partite sets, I can only ever find paths of sorry, I said that backwards. Any two vertices in the same partite set, only paths of even length. And so that's, there can be, I think I said it right. There are no odd integers in the uniform spectrum. And then you can find paths of odd length between vertices in opposite partite sets, right? 1 or 3 or 5, I can get those there. However, there's no paths of even length between vertices in opposite partite sets. So so every even integer is not in the uniform spectrum. Hence, if G is a bipartite graph where each partite set has at least two vertices in it, then the uniform spectrum is empty. So one more example here are the friendship graphs. So these are cool. I'll draw the first few friendship graphs here. So these consist of some number of triangles, any number of triangles, identified at a point. So here is the notation differs. I'm going to call this, I'm going to use the order of the graph for this definition. I'm going to call this F5. So 5 vertices consisting of 2 triangles that have been identified at the same point. That's F5. So the friendship graphs only exist of odd order. Some people call these windmill graphs, but I call them friendship graphs because of a famous theorem called the friendship theorem. Here's F7, and so on. So you take some number of triangles and identify them all at the same vertex. These graphs are special in terms of uniform spectrum because they are 2 uniformly connected, but not k uniformly connected for any other value of k. So they're not one uniformly connected because they're not complete, right? An edge is the same thing as having a path of length 1. They are two uniformly connected. Any one of these is two uniformly connected, and you can do a quick check that between any two vertices you can find a path of length 2. But they're not three uniformly connected, because if I pick, say, this vertex and this vertex, two vertices in the same triangle, so like this one and this one, try finding a path of length 3 between them. Well, you can't. You'd have to go out to the central vertex, and then in order to get back to this vertex, well, you can't leave the central vertex to any other triangle and come back. That wouldn't be a path, and so you have to come back. So the only paths between these two vertices are of length 2 or less. And so it's not 3 uniformly connected, not 4 uniformly connected. It's not k uniformly connected for any other k. And so these friendship graphs are special in that regard. All right, so what's our conjecture on uniform spectrum? So when I researched this in grad school, I wrote a program that I actually used for a project while I was here at PFW. And what I was able to do is determine the uniform spectrum of all graphs of order at most 8. So I just wrote a brute force algorithm that would do this. And I noticed a very curious pattern. And the idea was, anytime I found a graph that had n-1 in its spectrum, so any graph that was n-1 uniformly connected, remember this is the same thing as Hamiltonian connected, then G also had n-2 in its uniform spectrum. It was n-2 uniformly connected. And this was true for all graphs of order at most 8. This was also independently proven, I believe, for graphs of order 9. Someone was able to show this, not brute force. But we weren't able to show it for any other orders, and we weren't able to show it in general, although it seems very likely to be true. But we have no proof, we have no disproof. So this would also make a very nice topic. You could look at some n-1 uniformly connected graphs, some Hamiltonian connected graphs, and show that they are n-2 uniformly connected, or you can try for an argument to show that, say, all graphs of order 10, this conjecture is true, something like that would be great. Now, there's another topic called the rainbow Hamiltonian connection number. This is another notion of connectedness that involves colorings of graphs. So connecting vertices by paths where those paths have some sort of property in terms of colors of the edges. So I'm actually going to leave this one until later after I've talked about edge colorings. All right, I'll see you there.